Okay, so I'll answer the first one. To Juan, the nice animations that Dave Kinney was presenting from VSP Aero. The version of VSP Aero that we distribute doesn't have that built in. Dave Kinney uses a different library for taking built-in screenshots, and I don't want to build and distribute that, so I rip it out. So he takes screenshots. I'm not sure whether he has that automated or whether he does it manually, and then he uses a command line program outside of that to stitch it together into a video. Well, I'll add that to the list. Maybe Justin, we should that list I sent you. Maybe we should add to it. We've been talking about getting it so that the VSP viewer uses the same library as OpenVSP, so that we don't have the library dependency problem that I've been trying to avoid, but we can get the videos back in. So we'll try and make that easier so that we can make those videos, because you're right, they're compelling for the unsteady cases.
Yeah, I agree. I'll add it to the list.
The next question, it is correct well, there's sort of two answers. If you're using OpenVSP's finite element structure modeling, each structure, each sort of assembly is built around one component, which is the trimming outer surface, the OML. And so you build a structure for the wing, you build a structure for the fuselage, you build a structure for the tail. You can even build multiple structures for a wing. You can have a primary structure, and then you can go back and have another structure for the flap and another structure for the leading edge. So those are not in the built-in VSP tool. Those are not in any way connected to each other or intersected with each other. You can do multiple of them and then export them separately, and then in your finite element tool, connect them together. And that's certainly one use for the key points that Justin was talking about, where you can use those key points to then insert rigid elements to transfer loads between those components. And that's often the way that you would do a model, because you probably don't transfer a load directly through the skin of a wing all the way to the skin of a fuselage. Instead, you have your primary structure that goes to some fittings, and those fittings are hard points on both sides, where you have ring frames and other things that come together to transfer load into those fittings, and then you're really trying to carry the load there. So on the other hand, the M4 Structure Studio does have the ability to model multiple structures, and they have the tool that they talked about for merging those structures together, merging and joining. And so those they do have that ability to do multiple structures. So it's a bit more sophisticated. There's a question about how to model liquids in OpenVSP, and specifically for fuel. So earlier today, there was a question about fuel tanks, and I mentioned conformal geometry as a way to do that. Let me do a very quick demo with conformal geometry, just to show a wing fuel tank. I know, Scott, you're a space person, so you'd rather put fuel tanks in cylinders, but we'll put it in a wing real quick. So here's a wing, and just for fun, I'm going to look at it as a transparent wing. And I'm going to go ahead, and we want a little bit more. For this, we probably want a bit more thickness. So I'm going to make it an 18% thick airfoil, just for that argument's sake. So here's a nice fat wing. And conformal components, if you pull this pull down, and it's this just above the line, if you choose conformal, what it does is it's a shape type that derives its shape from another shape. So when you choose conformal and you say add, what it does is it adds the shape as a child of it. So I'm going to go ahead and shade that, and I'm going to make our conformal component ruby, so it's nice and red. And what you see here is we actually have the red surface is an offset surface inside of the wing. And what we can do is, if we want that to be a fuel tank, we can come to the design tab and we can trim it. And so first we'll trim it in the chord and say we want that to be the minimum to be at 0.25. And so that would be our aft spar. and only go up to say 0.8. That would be our forward spar, maybe 0.85. We can get away with that. And then our fuel tank, maybe it doesn't start, so we're going to trim it in the U direction as well. It starts at say 0.2, and maybe it only goes outboard as far as 0.7. So we can do that to build a representation of a fuel tank in a wing. And then in this case, what I'm going to do is I will use sets to add that to set 0. And so now if I go and I do my comp geom, and I say I only want to do comp geom on set 0, and I execute, then it's going to come and calculate my volume of that component, 15.63. Likewise, I could come and say, okay, my conformal component, I'm going to show everything here. My conformal component, I'm going to increase its priority. We didn't talk about mass properties much, but I'm going to increase its priority, and I'm going to say that the density of my liquid, if the tank is entirely full, let's say the density of my liquid here is 3, and the wing is going to be a lower priority. It's stay at 0, and its density is 1. And so now if I do mass properties, and I do that mass properties analysis, what we've actually done is we've calculated the mass properties of the full wing fuel tank and the lighter density wing around it, and the total mass is 21, and the moments of inertia and the CG are all properly calculated. I've actually developed an algorithm to look at fuel tank mass, moments of inertia, and CG location as it fills from empty to full. So if you have some really strangely shaped fuel tank, especially say a wing with dihedral and sweep, if we come in here and we want to show all these again, if we come in and we put in a bunch of dihedral, we'll say, right? So let's crank it up 15 degrees of dihedral. You can imagine that and while we're at it, let's go truly nuts and let's put in a lot of incidence, 25 degrees of incidence. So you can imagine this wing, it has a very distinct, this fuel tank has a very distinct low point, this corner down here. And so as it fills up in the Z direction, you're going to have a center of gravity of the fuel that's going to start down here and work its way up to a centroid point, and it's going to follow some path, and the moment of inertia of that tank is going to change. So I've actually got some code that does that kind of calculation, Scott. If that's useful to you, we can try and prioritize making that available. It was a part of an earlier generation of mass properties revamp that never was ready for prime time and never got released. So let's see. So you can do, I'm looking at Sibin's question about a prescribed wake for the rotor. I'm not sure if Davis thought of that. I'll pass that on. We do find with experience that these VTOL vehicles, the interaction of the wake with the rest of the vehicle is one of the most tricky parts. So it might be useful occasionally to have a prescribed wake, but I think it'll also be, you'll find very quickly that it's limiting. If you are doing a isolated rotor, Justin mentioned this, if you are doing a rotor alone, then you might look at using the steady rotating frame formulation, which is documented on the wiki, or sorry, on the GitHub page, because that is a very computationally efficient way to do a rotor. Okay, so we've got a question about how do you fit model to fit an airfoil from a scanned wing or propeller, if it is possible. Thank you. So what I'd really just suggest, if you're trying to fit a full wing or a prop from a laser scan, worry about the airfoil last. What you're going to want to start with is getting the leading edge and the trailing edge correct, and getting the plan form right, and getting that shape. And I would go so far as to say, maybe really go to extreme lengths. Just ignore the fact, just use a NACA airfoil, get the leading edge matched up, get the trailing edge matched up, and get to where you're very, very happy with those. Once you've done that, sort of to Andy Hahn's point, once you're close on the wing, Fit Model's job is a lot easier. So once you're close there, then I would probably actually go and, if you knew it was one of the existing airfoil families, certainly use that family. But I would start by simply trying to match the thickness and get the thickness about right, and then maybe match the rest of the shape. And if I was doing that, I would use the Colfan, the CST airfoil type. That class shape transformation, if you're not familiar with it as airfoil types, this CST airfoil, this one allows individual sort of, we're at the root here. Let me move to the, sorry, we're at the tip. Let me move to the root. The CST airfoil allows the most localized control, and that'll be the best for some sort of a least squares fit to a cloud of points. So, but do that last. Get the leading edge and the trailing edge right, get the plan form really well matched, then match the thickness, then convert that foil to a CST, and then adjust the top and bottom surface individually to match.
And if I could add on to that as well, I think, sometimes it's hard to really back out exactly what the foil is, and maybe even a CST might be a bit too far in the other direction. If you're trying to just get it to where it approximates whatever the airfoil looks like, you can usually get that plan form out of either picking a NACA 4 series or a 6 series, whatever flavor you like, and just letting it float through some of those parameters as well. So if you find one that it's in a class of airfoil that is pretty darn close, you can play with far fewer parameters and get something really close to what you need. These are good questions coming into the live chat. Let's see.
Yeah. So Russ just asked about the lift equivalent area in the wave drag. So right now, I'd say there's no plan for that. You should be able to take and run the VSP Aero and Supersonic mode to get the nose to tail lift distribution, and from that compute the lift contribution to wave drag, which and also then the lift contribution to the sonic boom. We don't have any current effort on that at present. Certainly the pieces are there, and with the right people motivating and funding it, that would be something that would be possible. Okay. Justin, somebody has asked a question on the social Q&A about the Python API. They're getting a file not found, parasite.png, except it's spelled wrong. I'm not sure what on earth in the API would be trying to read in a PNG file. Justin, do you have any comments for that?
No, I don't think so. I'm not actually seeing the question either. Oh, I see it now on the conference IO. Yeah, I am not really sure what's going on there. If the user who posted that could provide some more information on exactly what's going on, is it when you try to import OpenVSP? Is it when you're calling a particular function? Everything like that. If you could provide that information, better place to post it might be on the Google group, but at the moment, I'm not aware of that error or how to solve it.
Okay, someone just asked, I was typing in an answer, but what airfoil family do you recommend for a tilt prop rotor I'll just say that historically, most propellers for propelling an airplane use either a 1/6 series or a 6/5 series or a combination of those two. Um, Most helicopter rotors use various rotors that are specific to helicopters. There aren't parametric families of them in the same way that there are the other NACA foils. Those airfoils are designed for lower moment coefficient typically, but they're also for very, very high, helicopter rotors, very high aspect ratio, very flimsy, very floppy, low solidity rotors. Tilt rotors are somewhere in between. The V22 uses a custom airfoil, and so yeah, Daniel Shield mentioned that. The XV15, there's a lot of airfoil data available about the V15 airfoils that NASA developed with Bell before the V22, and that rotor went through many revisions from the beginning of the development program to the end. There's a book by Harris, a NASA publication by Harris, that is a compendium of hover test stand data for props and rotors that includes a lot of those different steps in the XV15 rotor that specifies the foils used in them. So I recommend you look for that report by Harris. The early ones used, like I'm saying here, a 1/6 series and 6/5 series. The later ones went to proprietary airfoils that were developed by Bell.
Okay. Yeah, Justin, he said he was running the test digengiom.py, so I see that there's an answer to that already.
Yeah, I posted it in there. Really not sure about that one still. I would suggest, just opening up a Python interpreter, making sure first you can import OpenVSP, and then from there just try like a simple function call, like vsp.addgeom with wing. If that's all working, then it's probably a bug in that specific Python example that we could look into. But try those out first.
So I've got a question. I'm not sure who, since it's on the social Q&A, I'm not sure who's asking it, but I mentioned on one of these platforms earlier in the workshop that Uber has, and I have this idea of a community-built tool validation project, and I mentioned that as something that's hopefully in the works and coming. So the idea of this project would be an open source project. It'll be on GitHub. But instead of focusing on source code, it'll focus on aerodynamic test cases. And since Uber would be doing this, it would be mostly focused on UAM test cases. And the idea would be that we would provide the geometry, the input files, and the test conditions for different tools to be compared, and then leave it as an open project so that developers of different tools, whether that's Flightstream or VSP Aero or Charm or RCAS or high fidelity CFD tools or students at a university or whoever's developing aero tools trying to meet these UAM aero modeling challenges, would be able to use their tool on the test case and then push that result up as a contribution to the GitHub site. And the idea would be that they would not only put up their results, but they would also put up the input files so that it would also become a self-documenting set of best practices where the developers of these tools sort of show you how they would use a particular tool to tackle a particular problem. And the idea would be that we would add, it would be a growing list of projects that would start, and it would include everything from simple rigid body, fixed wing, stability and control type things like we saw some of today, all the way up to very complex interacting unsteady flows with rotors. And then, as I said, it would be a place for tool developers to go and show off what their tool can do, and also a place for the UAM community to sort of pose challenges and show the kinds of perhaps weaknesses that current tools have, because there's so many unique needs from UAM that it would hopefully help drive and motivate the tool development to conquer some of these challenges. So that's the idea.
All right. Let's see. Yeah, there's still some going around with the API stuff on the social Q&A. Watching the live chat to try and see if there are any other questions here. We've got just under 10 minutes before the scheduled close of the workshop, so I guess now's as good a time as any to thank everyone for your attendance and your participation in these events and these talks. We really appreciate that you've taken the time to see what's going on and to give us some feedback and to ask the questions and show us what you're interested in. So we really appreciate that, and hopefully you had a good experience this year. We were doing our best to try and pivot away from an in-person event, which is traditional for this workshop, and hopefully you've had a good experience and everything came through relatively clear. But we'll see what happens next year. I think that we've shown that we can at least leverage the technology that we have to try and make this reasonably accessible and easy to do here. So again, thank you to all of our presenters for giving your time and your dedication in trying to make this a really successful event. And I know I really enjoyed all of the talks showing what everyone has been doing with OpenVSP over the last year, particularly the cool features that everyone has done. So a big thank you to all of our presenters, and of course to Rob and Justin for helping me organize this event and to scheduling everything out. So big thank you to everyone for that. But unless Rob or Justin, either of you guys have any closing remarks, we've got a few chats coming in, and we really appreciate all of you as well. So
go ahead, Rob. Thanks for everyone for hanging with us. It's been a long 3 days. If you have the opportunity, do go over to the attendance survey. Let us know who you were, where you're from, who you work for, what your interests are, and we'll appreciate that. And otherwise, we'll hopefully see you in person at the next one, and maybe find a way to stream it as well.
Yeah, and I was just going to add real quick, thank you, Rob and Brandon. You put a lot of work into this. I think it turned out really well. The OpenVSP community, I'm sure, is very grateful for getting this all set up and everything. So thank you very much.
It's a great tool. I think that it's incredibly versatile and powerful, and for where it lies in the design space, it ticks all the boxes, and it just keeps getting better, and that's the great thing about it. So what a few days it's been. But everyone out there that's following along, thank you again for watching, and we really hope you enjoyed it. By all means, stay safe. That's kind of the name of the game right now. So take care of yourself, and all of these sessions are recorded and stored. You can follow the session links to get back to any of the replays to the videos, including the live chat. The videos themselves will be hopefully broken up into different sessions so you can quickly link to it. But follow the Workshop 2020 page for updates on how to find the information quickly, and we'll be sharing some slides and documents that we can get from the presenters so that you guys can have those as well. So with that, it's 5 minutes to closing time. There's no problem at all with finishing just a little bit early. So thank you, everyone, and stay safe. We'll see you around.